All right, so we're going to begin our journey through chapter 3, which is called Gravitation and Motion. It'll start out dealing with a little bit of contributions from Galileo, who we talked about in the last chapter, but really the central person here and the central contributions are going to come from Isaac Newton. In particular, his universal law of gravitation, as you're going to see. All right, so this is actually one of the results of Isaac Newton. Surprisingly enough, he had worked out the details of how fast it takes for an object to leave a planet and never come back. Right? I mean, you throw an object up in the air, and during Newton's time, and certainly for since more than 100 years ago, objects always came back. They always came back down. And so Isaac Newton actually worked out the details. I mean, long before it was technologically we were capable of doing this. Of how fast it takes to leave the Earth or any planet and not come back. And so that's called the escape velocity. All right. It's different. It depends on what the size of the planet is and what its mass is. All right, we'll get to that a little bit later, towards the end of it's towards the end of the chapter. All right, so Galileo had this idea of inertia, and so these are some of the ideas that Galileo came up with as far as what inertia is. Inertia is when a body is at rest, it'll remain at rest. When a body is in motion, it'll continue in straight line motion. All right, so it's a little more complicated than that, but that was initially his thoughts on it. He did some experiments with inclined planes, and we're going to see that in just a little bit. All right, so this is this very, very soon. So this is not exactly his experiment, but and of course Isaac Newton, who is basically a generation after Galileo, adopts this idea of inertia, and in fact makes his first law of motion. So these laws of motion, there's three of them that we're going to cover. Well, there's three of them, and plus the universal law of gravitation. So the laws of motion are general laws of motion, right? That's nothing to do with whether you're on Earth. You can be anywhere in the universe. So these are general laws. All right, and actually, one of the things. Let me just state this. One of the problems with Aristotle, and I know we're going back 2,000 years with Aristotle, but one of the problems is that Aristotle really gets hung up on friction, and he doesn't really understand friction as a force, and doesn't even think of it as a force. All right, Newton, however, does not, and is able to make great advances in physics, and of course in astronomy as well. All right, so here's a ball rolling along on a nice flat surface. So the length of the arrow indicates how fast it's moving. So as long as it's moving along on the flat surface, it's going to move in a straight line with the exact same speed, also the same velocity. So the velocity and speed are related to each other. However, velocity is a little bit more complicated. It deals with the direction that objects take. All right, so that's actually really important in astronomy. All right, so notice when the ball is going down the inclined plane here, the speed is increasing, right? So there's the speed. In a moment later, the speed is increasing and increasing until it gets to the bottom, right? And then it, let's say it makes a nice smooth transition here. And then as long as it's moving in this on this flat surface, it's going to go in a straight line with exactly the same velocity, right? These lengths are exactly identical. Then it starts to go up the inclined plane. And by the way, this is almost exactly Galileo's experiment. Newton performed these experiments as well, but Galileo had done it first. All right, so anyhow, when the ball starts to go up the inclined plane, it begins to slow down. Let's see, the arrow is the longest at the bottom, and then it gets smaller and smaller and smaller, and it will eventually come to a stop. The ball will come to a stop, and then, of course, roll back down the hill. All right, so anyhow, or actually, that's a good. Let me just state that as well. All right. One of the big things that Galileo realizes is that if where the ball stops on the other side, let's say it goes a little bit past this and it stops like right here where I have the mouse, it'll roll back. And it'll roll back to the same height as long as there was no friction. So even Galileo starts to think about this idea of friction, but Newton really takes that and develops some serious physics with it. All right, so a body continues in straight line, uniform motion unless it's made to change by a force. Right, so during this time it's moving in a straight line. It's accelerating. This is the first time we're using that word. Acceleration is the change in velocity. So it can be So this is a positive acceleration. Over on this side of this incline, the ball is going slower and slower. So that's a negative acceleration. Anytime you hit the gas in your car, you're speeding up. That's a positive acceleration. Or you push down on the gas, you're accelerating. And then when you push on the brake, of course you are also accelerating, but you're accelerating it in a negative sense. You're slowing down. All right. This part right here is like it's coasting. Right. That same thing is going on right here, where there's no change in velocity. Therefore, there's no net force on the object, right? That's an important idea, actually. We'll get to see that in just a second, or a couple of seconds. Oh, yeah, right here. Okay, so this is actually develops Newton's first law of motion in a little bit more detail. All right, so why is this box at rest, for example? If the guy here on the left and the lady here on the right push with the exact same force, then the two forces will add up to zero, right? And so when that happens, the object will remain at rest. In other words, you can have an object with multiple forces acting on it. In fact, some infinite number of forces. But as long as there's no net force, so the net force is like an unbalanced force. Here's an example of the unbalanced force, right? If she pushed a little bit harder, right, this force, this green arrow would be greater, and then the box would start to slide to the left, right? So that's not happening. And so there's no net force. The forces are adding up to zero. All right. So that's what this is all about. All right. So of course Newton's second law is what happens when the forces don't add up to zero. All right. So that's we'll get to that in just a second. All right. So astronomers. So this is another contribution that Galileo gave us. I mean, he does come up with the Newton's first law of motion, called the law of inertia. But another thing that Galileo does is when he starts doing these experiments with with projectiles, objects thrown into the air and then landing somewhere, and also a ball rolling down these wooden planks, very very much like this. All right. So Galileo's doing these experiments, and he realizes that that gravity is what is responsible for. Here, let me go back to this picture real quick. Um, what's going on? Why is this thing accelerating? Why is it undergoing acceleration? And it's really gravity that's doing it, right? So gravity is reaching up, as it were. You want to imagine that it's this force. It's a force of attraction, and so when there's gravity on the ball right over here, but there you have this object that is in between the ball and the earth, and so it can't go down. It doesn't go down until it falls over the edge here, and so once it does, it begins to accelerate, and then of course when it's going up the incline, gravity is slowing it down. All right, so we'll go back to Galileo. So with these experiments, he realizes that that gravity could also, or he hints at it. He hints at that gravity could affect astronomical motion, right? Because remember one of he's a full. He believes Copernicus, that the planets go around the sun. In fact, he shows very strong evidence that the planets go around the sun with the phases of Venus, and so he realizes that if that's taking place, there must be a force. I mean, even Kepler, who was a contemporary of Galileo, thought that there must be a force that is causing the planets to go around in a circle, or in an ellipse, or in an elliptical orbit. But Galileo actually got it right. It was gravity. I think. Kepler thought of it as magnetism, because somebody had been studying magnetism right around the time of Kepler, or right before Kepler. All right, so this is what we this is part of what's the modern scientific method. You come up with ideas, that you observe nature, you come up with explanation, and then you perform experiments. Okay, these are some of the experiments that he performed. All right, so this idea that gravity, left. It was a force that leaves the Earth, or that is influential in the orbit of the moon, or the motion of the planets, was completely alien to ancient humans. They never imagined that there was such a that gravity could influence they just thought it was some local thing, and didn't really think anything else about it. All right, so gravity is a force that causes the planets to constantly change direction. So that's the other thing. All right, so let's see. Was this? Let me just. I'm just looking forward just a little bit. All right, so this is actually getting into what's called Newton's second law of motion. All right. So Newton's second law. Oh, hold on, did I skip it? Maybe we didn't quite get to it yet. I'll in the next video I'll find where that is. I don't think I skipped it. No. Okay, so we're still on Newton's first law. All right. So the big thing here is that there's a force, and it causes the planets to constantly change direction. Right, and that of course is the force of gravity. If somehow there was a switch on the wall and you could turn off gravity, which you can't, by the way, the planets would just travel in a straight line out into space. But that, of course, doesn't happen because of the sun.